Today is the second class on liquid extraction, and it is a very important downstream technique. That is why I am spending more time on this, and today we will also look at some problems related to liquid extraction. So, in bioprocess liquid extraction plays a very important role. Immediately as soon as you filter the solids, you may resort to liquid extraction to recover your product. Okay. It could be a metabolite, it could be a protein or enzyme and so on, but there are many issues here in biological systems because the feed will be highly viscous. The feed that is coming out of a fermenter broth is going to be very highly viscous, and then there could be low difference in the density between the aqueous feed, that means the fermentation broth, and the solvent which you are using. That is another problem. The solid content could be very high because we are talking about dead biomass, live cells, broken cells, precipitated solids, because you get a lot of solids from salts and media components, presence of surface active agents like biosurfactant and other material which may be creating froth. So, because of all these reasons you may have problem in extraction, but then extraction is one of the best methods in biological systems. Like I said, your proteins, carbohydrates or even enzymes may be very thermally labile, and you might not be able to use techniques like distillation or any other high temperature operations, whereas liquid extraction you can work with room temperature and even with buffers actually. And sometimes part of your product also maybe get lost because presence of solids which may absorb some of your product. Like if you remember in our early days early lectures, I did a problem on how some desired product may get absorbed by the filter cake and get lost also. So there are contactors. I think in the previous class we saw different types of contactors, the mixer settler type of contactor, then I discussed a lot about the column type of contactors, that means vertical columns which occupies less space. Then centrifugal contactors is another approach where you can get very high mass transfer, dispersion, so that the transfer of solute from the feed into the solvent becomes very facile actually. So, centrifugal contactors occupies less space and they can be operated in counter current manner actually, and the contact time could also be very short time. So, you can minimize even the degradation of labile products using this actually. So, you can have a disc stack type of contactors. I talked about it and I showed pictures of disc stack centrifuge. So, similar disc stack systems can be used for liquid extraction also, or you can have multi-stage differential contactors. So, you can have several contactors in many stages. So, centrifugal contactors are becoming quite popular if you are interested in short contact time, if you want to achieve very high mass transfer and very high dispersion of these two liquids when compared to the traditional tower or the normal mixer settler type of contactors actually. So, operating mode of this extraction, it could be a batch or it could be continuous. Okay. So, the batch extraction could be single stage or multi-stage, continuous could be co-current or counter current. Okay. In the single stage you may be adding fresh solvent, in multi-stage also you may be adding fresh solvent. So, we will look at each one of them little more in detail. So, in the batch extraction you have the feed and you have the solvent, they get mixed up and there is an equilibrium that takes place. The solute moves from the feed into the solvent because of the high partition or high affinity. So, generally the partition coefficients have to be quite high, and the raffinate goes out which will have less amount of solute when compared to that in the feed, and the extract, that is the solvent, will contain a lot of your solute. Now, you can have another stage and so on actually. Okay, now our goal is to find out how much get extracted. Okay, in order to do that there are two different methods are there, analytical method and the graphical method. We will look at each one of them little more in detail. So, the first step when you are doing analysis of a single stage extracting unit, we have to do a mass balance. As I said before, mass balance is very important. So, you have the feed, okay, or the broth or the aqueous stream, it contains XF, the concentration of your solute. Now, you have the solvent S, it is coming at S flow rate, and the concentration of the solute could be Y naught. They get mixed up here and they get separated. So, the feed goes out at a flow rate of F and the concentration of the product could be XR, concentration of your solute could be XR. Now, the solvent has picked up some solute, so the concentration may be Y1, which is greater than Y naught. So, if you are adding fresh solvent, obviously Y naught will be 0 here, please remember that. So, we can do a mass balance of this particular unit. So, 2 input is equal to 2 outputs. So, mass balance for the solute F into XF, okay, F into XF plus S into Y naught, that gives you F into XR plus S into Y1, correct. So, if your feed solvent is fresh, that means it will not have any solute, then Y naught could be 0, then you will have only this term and these two terms, this will not be there. So, it is very simple. So, when you do this mass balance, okay, and we will assume Y naught is equal to 0, that means the feed solvent does not contain any solute and these two components are immiscible, that is very important, okay. They have to be immiscible, otherwise you may lose solvent, some solvent in the feed that is going out. So, you are going to lose solvent. So, if you take Y naught equal to 0, you end up with 3 terms here, F XF is equal to F XR plus, instead of here instead of Y1 we are putting this in terms of the partition coefficient into XR, because partition coefficient is Y1 by XR, that is the concentration of the solute in the solvent phase divided by the concentration of the solute in the raffinate phase, Y1 by XR. So, what we are doing, instead of Y1 we have replaced it with K into XR here. So, you can bring the XRs together. So, XR is equal to F multiplied by XF divided by F plus S into K. So, if I divide throughout by F, what will have, XR is equal to XF divided by 1 plus E. E is something like an efficiency factor where E is equal to S into K by F. S is the constant, the flow rate of the solvent, F is the flow rate of your feed or the flow rate of the broth, K is your partition coefficient, okay. So, E, and E has to be greater than 0, sorry, greater than 1. So, XR is equal to XF by 1 plus E. So, obviously XR will be less than XF, okay, that is what you expect, right. XR has to be less than XF because the solvent has picked up some of your solute. So, fraction extracted will be, the fraction extracted will be, okay, XF, that is the feed, minus XR divided by XF, right. XF is the concentration of the feed, XR is the concentration in the outgoing raffinate divided by XF. So, that is equal to 1 minus, okay, XR by XF. So, if you take this and substitute here, you will end up with E by 1 plus E. So, fraction extracted is E by 1 plus E, it is very simple to calculate, right, and E is equal to XK by F. And if you want to know how much of solvent I will require S to extract certain amount, I just have to rearrange this. So, I will get an equation like this, S is equal to F by K XF minus XR minus 1. So, all these equations are very important and we are going to do some problems using that equation. If K is large, that means most of the solute will be extracted into the solvent, okay. If K is large, obviously your E will be large, okay. So, the extraction efficiency will be also very large, correct, okay. So, what do you do in graphical method? So, in the first method, okay, analytical method, if I know these terms like F, S and K, I can calculate E and then I can substitute into this and then I can calculate what will be the XR. So, I can get the fraction extracted and so on. In the graphical method for batch extraction, we draw a graph where we have on the x axis the mole fraction in the raffinate, okay, and in the y axis we have the mole fraction in the extract, okay. So, there are two lines that will come, one is the equilibrium line that is K is equal to y1 by y1 by xr, that is the equilibrium line, and it will be a straight line passing through the origin. The other one will be the operating line, which corresponds to the mass balance. If you remember our old mass balance equation, we just have to rearrange little bit here. So, you end up having y1 and xr. So, as the mole fraction in the extract keeps going up, that means as the more solute is taken up more into the solvent, we will have less of the solute in the raffinate, and if the mole fraction in the extract is less, obviously there will be a higher concentration in the raffinate. So, that is why you have a straight line that is going down like this. So, these two lines will cut at some point, and this is the your condition at which you are operating, corresponding to both the mole fraction in the raffinate as well as mole fraction in the extract. Help of calculators or computers, we can quickly calculate them. When there were computers were not there, then people resorted to this type of graphical method. Suppose so you can have multiple stages. So, every stage I add some solvent. So, you have a feed, you add a solvent, and then you are extracting. Then that raffinate is going to the next stage, then again you add some solvent, again it gets extracted, like that it keeps on going. You may have many number of feeds, many number of stages, and you may be adding solvents many stages. So, the final XR, that is final concentration of the solute in the raffinate, will be equal to XF, that is in the feed, divided by 1 plus E raised to the power n. N is the number of stages. Now, this is called a cross flow system, because your feed is going in this direction, solvent is added vertically, right, that is why it is called a cross flow. So, the final XR will be equal to XF feed divided by 1 plus E raised to the power n. So, when n is equal to 1, you will get divided by 1 plus E, right. So, the advantage of this equation is tremendous. So, if I want to know how many stages of cross flow I should have, if I want to extract 99%, then I can use this equation. If it is 99% extraction, your XR will be 0.01 of XF, correct. Then if I know E is nothing but the efficiencies which I talked about. If you remember this, E is nothing but Sk by F. So, I know S, I know F, I know K, and I can calculate E. So, from there I can get the number of stages. So, this is a very powerful equation for calculating the number of stages required, for example, to recover 99% of my solute in n stages of cross flow. In fact, that is what this problem is. So, I have a solute in the fermentation broth 6.8 milligram per liter. So, this is your XF, quantity of the broth is 82 liter, this is your F. 1 liter of solvent, this is your S. Partition coefficient is 170. So, what is the fraction extracted? First I need to calculate XR, I know XF, and then I can calculate fraction extracted. So, what is the formula for fraction extracted? Just recall. Formula is E by 1 plus E, right. So, I need to calculate E is equal to Sk by F. S is given by 1 liter, K is given by 170, and my F is given by 82. So, I get E as 2.07. So, I have told you that E is generally greater than 1, then only you will get some extraction done. So, I put E divided by 1 plus E, that gives 0.6, that is 67% extracted. Now, I am sending it to another stage, and again I am adding 1 liter fresh solvent. So, what do I do? How much is the extracted? So, now I have 2 stages, I am adding 1 liter in the first stage, 1 liter. So, I can use the previous formula. If you remember, XR is equal to XF divided by 1 plus E n. Here n is 2. So, I can use that formula, right. XR is equal to XF divided by 1 plus E 2. I know the E, I know XF is 6.8. So, my XR becomes 0.72. Fraction extracted is 6.8 minus 0.72 divided by 6.8. So, it becomes 0.89, 89%. So, in the first stage I am extracting 67%, second stage I am overall I am extracting 89%. So, it is good to have 2 stages. But of course, I have used 1 liter solvent in the first stage and another 1 liter solvent in the second stage. Now look at another problem. It's a very interesting problem. I have K here given, a feed is 25 mg of solute, that is my F. How much could be extracted with the equal amount of organic solvent? That means if I take 25 mg of an, that is S solvent, how much will I be able to extract? It is very simple. I just calculate E and then E is equal to Sk by F. Okay, so that is equal to say 10 here, and then I substitute, I get XR as 2.27. So percentage extracted, that is I am having 25 initially, XR is 2.7, so I am extracting 91. Now I am dividing the same 25 into 4 parts, okay, 25 by 4, that is equal to 25 by 4 is 6.25, and then adding into 4 stages. Then what will be my extraction efficiency? So here my S will become 6.25, K will be same, F will be same, so my E will come down, but then my equation is different. I will use XR is equal to XF divided by 1 plus E raised to the power 4, do not forget that. Okay. So my E has come down by 4 times because I have divided, but my equation denominator has become 4, so my XR has become 0.166. So percentage recovery is 25 minus 0.16 divided by 25, so 99%. Very interesting. So you look at the previous one, if I take 25 mg of solvent and use it in one stage, my recovery is 91%, but the same 25 if I divide into 4 parts, that is 6.25 milligram, and do 4 times extraction, my efficiency is 99%. So what does it tell? It tells us, instead of dumping all the solvent in one stage and trying to recover, if I divide it into 2, 3, 4 many stages and use part of this solvent, my recovery is going to be better. That means multiple stage extraction is more efficient than single stage. So I have used same amount of solvent, okay, that 25 milligram, but when I divide it into 4 parts and use it as 4 stages, my recovery efficiency is much better. Okay. So this is a very important point to keep even when you are doing experiments in your lab. So do not dump all the solvent and try to extract, divide that solvent into maybe 2 parts or 4 parts and use little bit extract, remove, extract, remove, extract, remove, extract, remove, your efficiency will be much higher. Okay. Now another problem, let us look at. Here we are going to calculate the stages. You want to extract 95% of the protein, that means my XR will be 0.05 of XF. Okay. The quantity of broth, F is 100 liter, 2 liter solvent, F is 100, S is 2 liter, partition coefficient K is 200. Okay. So if I want to extract 99%, okay, then what happens? My XR is equal to 0.01. Okay. So I can use the same equation here, I am calculating N. Okay. So 0.01 is equal to 1 by 1 plus E raised to the power n. 0.01 is equal to 1 by 1 plus E raised to the power n. E is equal to Sk by F. So S I know, okay, S is 100 liter and K is given here, okay, K is given as 200, okay. So okay, sorry, solvent is 2 liter, F is 100 liter, K is 200. So when I substitute, E comes out to be 4. So from these I get as N is equal to 2.86, right, sorry. So I get N as 2.86. That means I need 3 stages if I want to recover 99% of extraction. Okay. If I want to extract 99%, if I am using 2 liter solvent and broth is 100 liter, K is 200 liter. So this is a very important data in an industrial scale. So I want to extract 90%, 95%, 99% of the material. Okay. So how many stages I should put in? So in order to understand, I need to calculate E, then I substitute into this. It's quite a simple equation which I got, and I substitute into this equation and I get the result. Okay, this is called cross flow. Cross flow, what do you do? Every time you are adding the solvent, it could be fresh solvent or into each stage. Okay. So the your feed flows stage 1, stage 2, stage 3, stage 4, whereas solvent is entering independently in each of the stages. That is called the cross flow extraction. Okay. Analogous to cross flow, we can also have co-current as well as the counter current type of operation. This is called a counter current operation. So, you have multiple stages here. Your feed may be going from stage here, 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 here and right down to 1. Your solvent may be coming from stage 1 to 2 to 3 to 4 to 5 up to n. So, feed is flowing in one direction, your solvent is flowing in another direction, that is why it is called counter current. So, final raffinate is coming here, whereas solvent is coming here. The solvent here could be very fresh, but then solvent coming here will not be fresh, it may be having some amount of solute because it has picked it up from stage 1 and so on. So, the concentration of solute will keep increasing in the extract as you move from the right to left. Okay. Whereas, in this case the concentration of the solute in the feed will keep going down as you move from stage n to stage 1. Analogous to counter current, we can also have a co-current, that means both are flowing in the same direction, okay, unlike the other one, and you can prove that co-current operation is not efficient at all when compared to counter current. I will leave it to you to prove that that co-current is not efficient when compared to counter current at all. Okay, let us go back to counter current. So, in a counter current the feed moves in one direction, your solvent moves in another direction. So, we can do mass balance for each stage and prepare a overall global mass balance. When you do that, okay, when you do that you get a relation, it looks very complicated, okay, XR, that is the final concentration of the solute in the raffinate, XR, XF is the concentration of the solute in the feed, feed is going like this, is equal to E minus 1 divided by E n plus 1 minus 1. Okay. Now, E is again calculated using Sk by F formula. Okay. S is your solvent coming from this side to this side. So, feed is coming from this side to this side. So, solvent keeps picking up material. Okay. So, it is XR is equal to XF E minus 1 divided by E n plus 1 minus 1. Okay. So, there is a difference between the previous and this. In a cross flow we have XR is equal to XF divided by E plus 1 or 1 plus E raised to the power n here, whereas the equation is different. The assumption here, K is the same in each stage, that means it does not change irrespective of the concentrations, K does not change. So, K remains the same in all cases. Okay. So, I can adjust this equation to get a relation for n also, that means if I want to find out how many stages I can do that also. So, this equation is very important. I will just do a problem. Okay. We want to extract 99% of a protein in a continuous counter current extractor, rate of heavy is 450 liters per hour F. It is extracted by a solvent 40 liters per hour S, partition coefficient is 60. Okay. So, E is equal to Sk by F, 40 multiplied by 60 divided by 50, that comes to 5.33. So, I want to know how many stages. So, I can use this equation. I want to extract 99% means XR is equal to 0.01 XF. So, 0.01 is equal to 5.33 minus 1 divided by 5.33 n plus 1 minus 1. So, all I have to do is calculate n, simple. So, I use this equation and I do that. So, when I do that I will get 3 stages. Okay. So, I need 3 stages of counter current liquid extraction to recover 99% of a solute when the E is 5.33, very useful equation. Okay. Similarly, just like counter current, we can have also something called multi-stage cross flow extractor. Okay, I want you to look at how this looks like as against this one. So, here you have only 2 streams. Okay. So, you have the feed or the heavies or the aqueous goes like this, XF is here, XR is here, you have the solvent coming here, fresh solvent entering and going all the way down. okay, and going there. Okay. So, that is how both of them look like. Okay. Now, whereas the next one, next setup, this is called a multi-stage cross flow extractor. So, we have the feed entering from the middle, FXF, and so we have a stream, aqueous stream, it is called Q, solvent is coming from here. Okay. So, here after this the quantity increases F plus Q, okay, because feed is coming with a flow rate of F, and you are having another stream of heavy, the Q. So, Q does not contain any solute. So, please note that, that is why we have not put any term here, Q does not contain any solute. Okay. So, after this stage you are going to have F plus Q, that is the total amount of the heavies or the aqueous stream or the raffinate flowing like this. Okay. So, the solvent goes like this and then goes like this, and finally you get the extracted solute. So, this is called a multi-stage cross flow extractor with, okay, solvent is added only in one stage. Okay. The normal cross flow solvent is added in each of these stages, whereas here it is added only in one stage. So, you also have an equation for this type of setup also, combining XR versus XF versus E, and please note you are going to have two types of E's here, one E for this side of it, because normally when we calculate Sk by F, okay, here we have the heavy flow is only Q, and when you come here this side the heavies has two flows F plus Q. So, you will have one E and you will have another E. So, we can call this one E and another one as E dash. So, that is because your F changes from here to here, that is F means, when I mean F is the amount of the heavies or the amount of the aqueous, amount of the feed changes here. So, E also will change for this portion of it as well as for this portion of it. Okay. So, those terms will come into the equation. So, still you can derive, but all these derivations are based on mass balance only. So, it is very simple, you have to do mass balances and you have to combine all the mass balances to arrive at a convenient equation which relates the XR, that is the concentration of the solute that is leaving the entire extractor, as against the concentration of the solute that is entering the extractor. Okay. So, I think with that we complete what we want to talk about on liquid extraction. Liquid extraction is a very powerful setup. Okay. Look, this is the equation, it looks very complicated, and as I mentioned there are two types of E's are there, E and E dash, one E relating to Q flow rate, another E relating to F plus Q. Okay. Thank you very much.